Um, okay, hello everyone. Hold on, I'm trying to find the right view here. For some reason, I speak and I only see Mike there. But anyway, hopefully the recording will catch me because this is kind of weird right now. So hello everyone. My name is Julie. I'm the director of the program Discover the Universe. Welcome to this webinar presented by my friend and colleague, Michael Reid. I will let him introduce himself in a minute. Just so you know, if you're new to Discover the Universe, our program is aimed at educators and we're there to help you teach astronomy. So we have different resources and training programs for you to become more familiar with some of the subjects or get the latest information. This is a bit the case today. Such an interesting topic. We're talking about possible life somewhere else or search for another Earth. That's the title that Mike is using, but I find it very interesting. I'm actually looking forward to getting the latest details as well on the subject. So yeah, again, for those of you who are live with us, feel free to use the chat to ask questions, and we'll probably have a open Q&A session as well maybe at the end. But if you have questions throughout, don't hesitate to write them down. And yes, so I'm happy to introduce Mike. Mike, for many years, actually was my main contact at the Dunlap Institute because Discover the Universe is offered by the Dunlap Institute. He's recently changed. He's now a full-time faculty teaching stream at the University of Toronto, but very happy to have him present today with us. So thanks, Mike, for being there. You're muted. It's like you've never done that before.
It's like I've never been on Zoom. Thank you so much for inviting me and for the introduction. So as Julie said, my name is Michael Reid. I'm a professor of astronomy at the University of Toronto. And today I'm going to tell you about the search for another Earth, or Earth 2.0, however you like to think of it. As Julie mentioned, I really warmly welcome questions at any point. I can see the chat. So if you want to, pop something in the chat, I'd be happy to answer things as we go along, and I will leave time at the end for questions if we don't get to answer them all as we go. Okay, so here we go. Our topic today is this incredibly topical thing in astronomy these days, which is the search for, generally astronomers would say exoplanets, planets orbiting stars other than the sun. But for most of us, whether astronomers or members of the general public, we tend to be interested in planets that are potentially Earth-like for all the reasons you might imagine. Maybe we could go there sometime. Maybe there's life on those planets. Maybe there's someone living there we could communicate with, all of these kinds of things. And for those of you who are teachers, these are probably the kinds of questions that will most inspire your students, right? They may be interested in the idea that, there's 20,000 Jupiters out there, or actually billions of Jupiters out there, but they're probably a lot more interested in the idea of another Earth. And as we'll go through today, first we need to define exactly what we mean by another Earth, and then we'll talk about, the search for such planets, and then I'll bring you as up to date as I can on the very latest findings from the most recent telescopes like the James Webb Space Telescope. Okay, so here is our home planet, Earth, right? This is the place where we've all spent, presumably, unless there are astronauts in the room, we've all spent our lives here on this lovely blue planet. And it's very familiar to us. This is the only time in this talk we're going to be looking or spending much time looking back toward the Earth, because as an astronomer, my job is to direct your attention outward, away from the Earth. But just for a moment, I kind of want to dwell a little bit on the Earth and think about what makes it special. So if you look at this photo, this is a very famous photo of Earth that called Blue Marble, that is often said to have kicked off the environmental movement. Because it's a very profound photo, right? We take these kinds of images for granted these days when you can pull up your phone and jump into Google Earth or your favorite mapping application. But there was a time when an image like this was really new. People had never seen our own planet from outside before. And in particular, to see it floating in this apparent void, you can't even see the other stars because of the exposure settings for this image. It just seems so fragile in a lot of ways, right? It's this life-bearing globe that is embedded in this immensely hostile environment. There are a lot of characteristics of the planet, we'll come back to those, that make it suitable for life. Okay, so let's flip our view around rather dramatically. This is a photo you may have seen recently. It's been in the news quite a bit from the James Webb Space Telescope, which is one of the most powerful telescopes, certainly the most powerful space telescope at the moment. And this photo is astonishing not only because, it's beautiful, but also for what it shows and for how it was taken. So this photo represents a tiny microscopic speck of sky. It's about the size of a grain of sand held at arm's length. So if you imagine, a tiny little speck of sand held way out at arm's length, that's about the fraction of the sky that this image covers. And nevertheless, you can see in the image, it contains thousands upon thousands of objects. You may not be able to make them all out individually, but most of the objects you see in that image are not stars, but galaxies. So each of those galaxies contains hundreds of billions or even trillions of stars. And again, this is a tiny speck of sky, not quite randomly chosen, but it's representative of what the whole sky looks like in every direction. So as astronomers, we imagine, in a universe that's like this, where there are billions of galaxies in every direction you look, and each of those galaxies contains billions of stars, and each of those stars could be orbited by several planets, starts to become hard to imagine that there wouldn't be at least a couple somewhere out there that are, Earth-like in some way. So that's what we're going to talk about. But let's think a little bit here about what do we mean when we say an Earth-like planet? What would it mean for a planet to be Earth 2.0? Do we mean a planet that is an exact clone of Earth? We want it to have 70% oceans, 30% continents, a nitrogen-oxygen atmosphere. Do we want the temperature to be roughly the same? How many things have to be similar for us to consider a planet Earth-like? Okay, in this graphic here, you're seeing a bunch of both real and imagined worlds. And I'm going to come back to some of these later on, but these are all kind of different visualizations of something that by some definition you might describe as Earth-like, okay? And yet they're all very different from one another. So when we think about, what makes Earth special and unique, well, fundamentally, the most obvious thing is just life, right? Earth has life, and no other planet we know of has life. So when we look for something that is like us, like our planet, life is the obvious thing to look for. There are some problems with that, scientifically, at least as far as looking for such a planet goes. One is that we don't actually know fundamentally what life is. You can look up a definition of life in a biology textbook, and it will list a lot of characteristics, but most of those characteristics are kind of hard to pin down over interstellar distances. So for example, commonly you might see that the basis of life is DNA. DNA is the thing that makes life life, right? This might be true. We might someday be able to come up with a general theory of life that is, means that all life is somehow based on DNA. Might not be true, but let's say it was. Even so, DNA is not something that's easy for astronomers to detect from, many light years away, from across interstellar distances. So it's probably not the most useful thing to look for when we think about looking for an Earth-like planet. If we want to make this search practical, we have to look for things that we can actually find using the technologies available to us. So when you think back to this image of Earth that I showed you, and you imagine, what in this image makes Earth special? What makes it hospitable to life, but also might be detectable from interstellar distances? So I don't know if anyone wants to pop in the chat. What do you see in that image there that, makes Earth Earth, and we might be able to detect on a planet that was very far away? Okay, one idea there. Anyone else? Okay, so Joanne said water, which is exactly what an astronomer would usually say, right? One of the things that makes Earth special is that it is able to sustain liquid water for long periods of time. And although water may not be absolutely essential for every possible kind of life that could exist, it is essential at some point in the life cycle for every form of life that we know exists on Earth. So it isn't itself the sort of basis of life, maybe, and the presence of water doesn't necessarily mean that there is life there. But as far as we know, for the types of life we are sure exist, they depend on water. And that means that if you can find planets that are capable of sustaining liquid water for long periods of time, you have gone a significant way toward finding planets that are Earth-like in some way. So astronomers, when we think about this, we use this concept you may have heard of called the habitable zone or the Goldilocks zone. And it's based on this simple idea that if you put a planet at different distances from a star, you could take the same planet. So imagine you take Earth. Depending on how far you put it from the sun, it would be more or less able to sustain liquid water. So if you put Earth very close to the sun, the water would all boil away, the atmosphere would be stripped away, and it would be boiling hot. If you put it too far from the sun, the water would freeze, the atmosphere would freeze. Again, no liquid water for long periods of time. You need the planet to be in some happy medium region, shaded in green here, which we call the habitable zone. This is the range of distances from a star where you could put a planet that was otherwise basically like Earth, and it could sustain liquid water for a long time. So this is what astronomers do. We look for planets that are in the habitable zones of their parent stars. And just for kind of due diligence, we need to start at home first, right, in our own solar system, and ask which planets are in the habitable zone of the sun, and are they actually habitable? So the first planet to consider is Venus. Now, Venus, again, by some definitions, is extremely Earth-like. It's about the same size as Earth, about the same mass. It's made of roughly the same things. It's made of, rock. It has a relatively thin atmosphere in a kind of geometric sense, right? The atmosphere turns out to be dense, but it's fairly thin. It's not a great big puffy atmosphere like Jupiter or Saturn. So in a lot of ways, you could say Venus is a lot like Earth. And in fact, when scientists sent the first spacecraft to Venus to explore it, they really thought it was going to be like Earth, to the extent that they did things like put flotation devices on some of the early spacecraft that were sent to Venus, expecting that when they got there, they would plummet into an ocean. And then, of course, they found out that that wasn't true. So why is that? If Venus and Earth are, in a kind of global sense, similar, why is Venus not habitable? Here are some properties of these two planets. So you have Earth on the left, an average surface temperature of about 15 degrees, right? The atmospheric pressure, we say, is 1 atmosphere. And the atmosphere is made of, at the moment, 0.04% carbon dioxide. All of those things are very different on Venus for one main reason. On Venus, the atmosphere doesn't have tiny trace quantities of carbon dioxide the way Earth's atmosphere does. I think, especially these days, we're sort of losing sight of that point. We're so worried, rightly so, about the increasing concentration of carbon dioxide in our atmosphere that we forget that actually there's very little of it in total. It's still a big problem if it goes up, but it's a relatively small fraction. On Venus, almost the entire atmosphere is carbon dioxide. It's like the nightmare scenario for extreme climate change. And as a result, the temperature on Venus is blistering hot, right? The atmosphere is almost entirely carbon dioxide. It's extremely thick, right? It's a high pressure atmosphere. And as a result, it's hot as an oven everywhere on the surface of Venus. So these early spacecraft, the very few that have survived long enough on Venus to return photos, show that it's nothing like Earth, even though it's broadly similar to the Earth. It's just too hot. The atmosphere is too thick. Okay, so now let's jump the other way. We'll go further from the sun and ask about the other, vaguely Earth-like planet in our solar system, which is Mars. So this picture, already shows you the ways that Earth and Mars are different. they're kind of similar in a lot of ways, in a way more similar than Earth and Venus are, at least in the ways that pertain to life. So again, if we compare their temperatures and their atmospheres, Mars has an average temperature around -60, which is cold, but there are places on Earth that are that cold and life can survive. It has a very thin atmosphere, barely any atmosphere. But again, like Venus, that atmosphere is almost entirely carbon dioxide. So even though it's extremely thin, it actually does a decent job of keeping Mars, relatively warm at its fairly big distance from the sun. So although Mars doesn't look a lot like Earth, it's a fair bit smaller, lower gravity, very little atmosphere. If you were to land on the surface of Mars, as we hope some humans will do in the next, decade or so, it doesn't actually look all that different from Earth. It's sort of a very cold desert. However, if you look closely in the picture, you will notice the total absence of anything that appears to be alive. We aren't 100% sure that there isn't some form of life on Mars, but if there isn't a lot of it. There aren't, trees and critters wandering around on the surface. So while it's possible that life could survive on the surface of Mars, as far as we can tell, it doesn't satisfy this criterion of having long-lasting liquid water on the surface. So that means that Venus and Mars kind of delineate the edges of this habitable zone around the sun. Venus is a lot like Earth, but a little bit too close, and therefore boiling hot. Mars is less like Earth, but it's far enough away and has just about the right atmosphere that the temperature isn't too bad. And still neither of them hosts life as far as we can tell. So what do we do with that information? Well, beyond those two planets, all of the other planets in the solar system are, as far as we can tell, wildly unsuitable. Mercury is, both boiling hot and freezing cold. The rest of the planets are not even a little bit like Earth. They're balls of liquid and gas, no solid surface analogous to Earth's surface. So they're not good candidates for being Earth-like. So that leaves other solar systems, right? That leaves looking for planets around other stars. But as we look into those solar systems, we should keep in mind Venus and Mars to help us, do what we call comparative planetology, right? We evaluate the kinds of planets we see elsewhere by comparing them to the properties of planets we know better from up close. So the search for planets orbiting other stars has been going on for a long time now. In fact, for literally thousands of years, people have wondered about this. Are there planets orbiting stars other than the sun? And I certainly remember very clearly when I was an undergraduate student studying physics and astronomy, the total number of planets orbiting other stars that was known after thousands of years of speculating about this and wondering and trying to find them was 0, right? It wasn't until the mid-90s that we first started discovering planets around stars other than the sun. We call these exoplanets. And in particular, I'm referring to planets orbiting stars that are like the sun. Technically, there were a couple of very strange planets known orbiting some extremely strange kinds of stars before this. But in terms of planets orbiting stars that are broadly speaking similar to the sun, there were none known as of 1994. But starting in 1995, we began to find some. In 1995, there were 3 discovered. And note that they were all, as shown in this graphic, they were all gas giant planets. So they were all broadly similar to Jupiter and Saturn. In fact, they were typically quite a bit bigger than Jupiter and Saturn. Not suitable for life, right? Mainly balls of liquid gas and a little lump of rock down buried deep in the center, probably, but nothing that would support life as we know it. But the search continued. By 2000, we knew of about 55 exoplanets. Again, still mainly gas giant types of planets. By 2010, the number was up to 591. And you'll notice here that in my representation of the mix of planets, they're getting smaller and smaller. So by the 2010s, we could find planets that were like Uranus and Neptune, sort of smallish gas giants, getting down close to more like the sizes of Earth-like planets. And certainly by today, in 2023, as of, right now, the number of confirmed exoplanets is 5,312. That's today's number, but it's going up all the time because this is a immensely active area of research. There are thousands of astronomers all over the world who are really keen to try and boost this number and find more planets for us to study. So with 5,300 exoplanets known now, and as our technologies have advanced, many of those are now sort of, potentially Earth-like. They're Earth-sized planets or even Mars-sized planets. We're able to find relatively small planets. However, and this is a kind of an important thing for explaining this to students. What people often imagine when astronomers say that we have found or detected an exoplanet, they imagine, we used a telescope, we pointed it at another star, and we took a picture of an exoplanet. This almost never happens. For technological reasons. It's extremely challenging to actually take a picture of an exoplanet. The main reason is simply that if you try, it's like trying to take a picture of a firefly sitting on top of a stadium light. Try and do that with your phone, put a little tiny source of light on top of an immensely bright source of light and try and take a picture of it. The image is just blasted by the bright source of light and you can't see the dim thing. So this is the problem we face when we try and take a picture of a tiny, tiny dim little object like a planet next to a blazing bright object like a star. Nevertheless, in very select cases, we have been able to do it. So this is a little movie of another solar system. In the center of that image where you see the yellow star represents the location of that solar system's host star, the equivalent of our sun. And you can see there's a lot of stuff around it. First of all, it's been kind of blocked out using, basically kind of a physical object to block the light from the star. And then there's a lot of digital processing that has to be done to the images to try and scrape out light from the star so you can see the planets. And lo and behold, in the background, you can actually see in this image 4 tiny little specks of planets orbiting this star. And you can see one of them quite far away and then 3 a little bit closer in. So those are genuine photographs of planets orbiting other stars, but they're nothing like the Earth. And in fact, we won't be able to take pictures of planets like Earth orbiting other stars for some time yet. These are gas giant planets. In fact, they're super big gas giant planets, bigger than Jupiter, and they're really far from the stars that they orbit, far enough that we can do this technique and scrape out the light from the star. Even the most powerful space telescope that we have today, the James Webb Space Telescope, can barely do this. So these are images of a single planet in different colors of light taken by JWST. And again, the little star icon represents where the host star is, and the kind of blobby object at the center of each of these images is a planet. And you can see there's no detail to be seen. We would say in astronomy that this is unresolved. It's just a dot. It's a single dot that tells you nothing about the planet. Or it tells you some things about the planet, but it doesn't tell you anything about, for example, does it have continents or oceans? Doesn't give you the kinds of information we would like. And again, this is not an Earth-like planet by any stretch. It's a very young, very hot gas giant type planet like Jupiter. So for now, with the telescopes we have available to us, this is the state of the art for actually taking pictures. And yet we know a lot about exoplanets. But not by taking pictures of them. Instead, most of the exoplanets that you will have heard of were captured, were detected using what we call the transit method. So the transit method is an indirect detection method. It works as shown in this little movie here. Basically, the planet passes in front of the star, and in so doing, it blocks light from the star for a brief period of time. So what we do is we take pictures of stars, many, 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 many pictures of the same star over and over and over again. And we look for pictures in which the star is slightly dimmer. Okay, and you can stitch those pictures together into a graph like the one shown here, showing the brightness of the star versus time. So as the star's light dims repeatedly, we can deduce that there is a planet orbiting that star. So for example, if you were aliens observing the sun, every year Earth would pass in front of the sun, and you would see a little dip in the brightness of the sun because of the light blocked by the Earth. So this is a fairly straightforward technique for finding planets. You just take lots of pictures of a bunch of stars and look for stars that have dimmed, and then ideally stars that dim repeatedly as the planet goes around and around and around. And as a result of this being a relatively simple technique, it has worked profoundly successfully. And of those 5,300 exoplanets we know today, most of them were detected this way. There are about half a dozen other ways of detecting exoplanets, but this is the most successful. So what are those exoplanets like? Well, every time I talk to people about exoplanets, the number that I could tell you about just goes up, 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 up. You know, there's so many exciting systems being found every day. So I'll give you some highlights, but feel free to ask about, you know, any particular kind of planet you might want to know about. So this is a kind of typical, potentially habitable set of planets detected by the spacecraft called Kepler. So what this diagram is showing you on the bottom level is our solar system, and then the orbits of the 4 inner planets in blue. So you can see Mercury, Venus, Earth, and Mars, the orbits of those planets. The green area is the habitable zone. So in this diagram, you can see that Venus is just on the inner edge of the habitable zone. Mars is just on the outer edge. But in the remaining diagrams on the top, for example, the one at the very top here, which has a tiny little red star, relatively cool little red star called Kepler 186, you can see that it's got a habitable zone which is closer to the star, because the star is kind of a cool star, so you have to be quite close for your planet to be warm. And in that habitable zone, there is a planet, which we call Kepler 186f, and it's about the same size as Earth. This little image at the bottom is an artist's representation, right? That is not a real picture. Again, we can't take these pictures, but through this transit method, we can work out that the planet is about the same size as Earth, and it orbits in the habitable zone. Similarly, here's Kepler 452. It has a somewhat larger rocky planet. This is a kind of planet we don't have in our solar system that we call a super-Earth. And super-Earths are really interesting because we don't really know what they're like. They might be, you know, depending on you know where they are and what their chemical composition and whatnot is, they might be Earth-like. They might just be like a gigantic Earth, or they might be totally different. You know, they may have totally hostile atmospheres. They may have incredibly thick oceans so that there's no land for life to crawl out onto, and therefore probably no life that's a lot like at least you and I, maybe aquatic life. And we keep finding more and more of these systems with planets in their habitable zone. So this is another fairly exciting system. This was discovered by a subsequent telescope to the Kepler telescope called TESS. TESS is a current telescope that is doing basically the same thing. It's looking for planets using the transit method, but it's specifically looking for planets that are orbiting bright stars and in particularly nearby stars. The idea being that we want to find planets that are close enough that we can study them in some detail and learn whether they really are Earth-like. So this planetary system, TOI, TESS Object of Interest, 700, right? Astronomers, very creative names for things. So this is TESS Object of Interest 700 system. It has a planet, which we just label them alphabetically in order from the star. So B and C are very close to the star, but D is in the habitable zone. What's interesting about this system is it's only 100 light years from Earth. So it has a sort of Earth-sized exoplanet in its habitable zone, and it's close. 100 light years may seem like pretty big, pretty big distance. And indeed it is. It would take us millions of years to go that far with our current technology. But it's incredibly close in astronomical terms. It's a tiny, tiny fraction of, the size of our galaxy, for example. 100 light years is really basically in our celestial backyard. So even though we can't go there and have a walk around on this planet right away, we can study it fairly well with telescopes. Even closer is the TRAPPIST-1 system, you may have heard, discovered several years ago. This planet has arguably 3 Earth-ish sized planets in its habitable zone, and it's only 40 light years away, so even closer. Very recently, there was announced another system. This is GJ 1002. It's only 16 light years away, so you cannot get much closer than that. There aren't all that many stars closer than that, and it has 2 potentially habitable planets in its habitable zone. This is, of course, an artist representation showing them to be, blue and green and lovely. We have no idea whether they're actually like that or not, but it gives you some hope that there might be something somewhere nearby that would be Earth-like. Joanne says, what is needed for an object of interest to gain a formal name? At the moment, astronomers discover literally billions of things a year, and we just can't. We do give them names, but those names are usually something like the order in which they were discovered or their coordinates on the sky, something like that. So you saw that both Kepler and TESS just number their discoveries. Kepler 1 is the first star it found, Kepler 2, Kepler 3. TESS is, 1, 2, 3 again. For them to get actual proper names, usually the way that's done, we don't bother for the vast majority of objects. You would never want to try and give proper names to, every star or every asteroid. But for planets, because obviously people have interest in this, we do actually try and do that. And the way it's been done recently is through the International Governing Body of Astronomy, which is the International Astronomical Union. And they run periodic contests for people to name exoplanets. And usually they try and, get schools and students interested in that and get them to, come up with a class suggestion for the name of an exoplanet. And then they, will submit these to the IAU and they'll be judged, and then they pick one to name the planets after. So there have been a couple dozen planets named that way by now. If you're interested in that, I know that Discover the Universe often publicizes these yeah, there we go. There's the link from Julie. So these contests are often publicized, and you can have your class contribute if you're interested next time there is one. They sort of run them every year or so. Okay, so there are now a couple of dozen exoplanets that are roughly Earth-sized and are in the habitable zones of their parent stars known. There are probably billions of them out there based on how many planets or how many stars we've looked at and how many we've found. It seems very likely that there are billions of these in our galaxy. But here's a synopsis of some of the most firmly in the habitable zone and therefore the most likely to be Earth-like that are relatively close to us. And as I say, there are a few dozen of them now, and this number just keeps notching up all the time. So this is really hopeful, right? We now have a catalog of planets that could be Earth-like that we want to study in more detail. Because remember, all we've said so far is that they are Earth-sized and they're in the habitable zone. But remember Venus. Venus is Earth-sized, to within a few percent. It's kind of almost in the habitable zone, depending on how you define the habitable zone. But it is in no way Earth-like, right? Boiling hot on the surface of Venus all the time. And the reason that it's not Earth-like is because of its atmosphere. So if we want to know whether a planet that, is broadly speaking similar to Earth, if we want to know, is it actually like Earth? Is it temperate? Is there water? What we need to do first is characterize its atmosphere. We need to know, what is that atmosphere made of? How thick is it? How much greenhouse effect does it produce? Is there water in that atmosphere, suggesting that there's water on the surface? Things like that. And this has been very challenging to do in the past, but James Webb Space Telescope is actually able to start giving us these kinds of measurements. So here's a very recent result from just a few months ago from the James Webb Space Telescope. This is a spectrum of the atmosphere of an exoplanet. So what it's showing you is the same thing as, when you take light and you pass it through a prism and you get a rainbow, it's graphing that same thing. So on the vertical axis, we have the amount of light, and on the horizontal axis, we have the wavelength or the color of the light. The colors that you're actually seeing on that graph have nothing to do with the color of the light. They're just shading different regions of the spectrum. But basically what you're seeing here is a measurement of the light being produced in different colors from the atmosphere of an exoplanet. And there are different features in this spectrum that correspond to different chemicals. So you can see labeled on here water, carbon dioxide, or rather carbon monoxide, methane, silicates, which are, things like sand. There are all sorts of things in the atmosphere of this exoplanet, including things that, suggest habitable environments like water. However, this planet is nothing like Earth. It's another one of these gigantic, young, super warm planets, more like Jupiter, even less hospitable to life than Jupiter. The fact that it's young and warm makes it produce a lot of light, which makes it easy to do this technique with, right? We can actually get light from the planet and do this technique, produce a spectrum, and thereby find the chemical fingerprints of different chemicals in its atmosphere. But for genuinely Earth-sized planets in the habitable zone of the star, we can't do exactly the same thing. We can do something very similar, though. It just doesn't look as good. So if you look at this graph, you can see that the graph is very, very detailed, right? There's tons and tons of little wiggles in the line. All of those wiggles tell us something about the chemistry of that atmosphere. Here is a similar graph, the same exact idea, but for an Earth-sized planet orbiting another star. So this is the planet LHS 475b. It's a roughly Earth-sized planet orbiting a star that's about 41 light years away, so it's quite close to us. And all of the white dots represent measurements of the amount of light being absorbed by that planet's atmosphere. And it's basically the same information as on the previous slide, but presented in a slightly different way. And you can see that there's not very much of it, right? There's just a few data points. It's not that beautiful, detailed, wiggly line. And it's not really obvious that it's telling us much, right? So what those colored lines show you is 3 different possible atmospheres for this planet. So people generate models of what could the atmosphere be like, and then they say, what would this graph look like if that planet had this kind of atmosphere? So for example, the green line is an atmosphere made mostly of methane. So this might, for example, be similar to the moon of Saturn called Titan, which has a kind of a methane nitrogen-ish atmosphere. And that doesn't look like it matches the data very well. The green line, doesn't go through most of the points. The purple line is a carbon dioxide atmosphere like Venus. And you can see it is a little bit more consistent with the white dots, right? The purple line kind of sticks to the white dots better than the green line does. And that suggests that this planet might have a carbon dioxide atmosphere like Venus. So you can see that this is really tricky to do, even with a super powerful space telescope like James Webb. We would really like graphs like this, but we can only get those for really big exoplanets. For small exoplanets, terrestrial or Earth-like exoplanets, it's still hard, even with James Webb. So James Webb will get better at this as it goes along and has a chance to take more data on more planets, but it's still going to be a little while before we are able to get clear measurements of the atmospheres of exoplanets, and therefore to tell whether they're genuinely Earth-like. Okay, any questions? Just take a pause for a sec. Any questions?
I'll come back for a sec as people are maybe writing questions. Thank you. Actually, this is very interesting. I hadn't been able to follow all the latest from James Webb, and this is very interesting to see the difference between a big planet and a small planet in terms of the details it can get. It shows how hard, like, we're really pushing the limits of what we can do. And anyway, I find that very interesting.
Great.
Also, I didn't know about I had seen the TOY. I didn't know what it meant. So I like the test.
That's object of interest. Yes, they all have their funny little designations.
I didn't know about that. I love their names.
Okay, well, while we wait for, in case anyone has some questions, I'll just give you a little bit of some kind of some closing thoughts that approach this question in a different way. Okay, so up until now, we've talked about Earth-like planets, but if you know much about our solar system, you may know that the majority of things that you might sort of intuitively identify with as planets, I'm being a bit vague, are not planets, right? So let me show you what I mean. So here's a picture of a thing in our solar system that we can see and study in great detail. I would say, if I was trying to be very careful, let's call it a world, okay? It is in a lot of ways like Earth. This object has oceans of liquid water, really big oceans of liquid water, like Earth. So it satisfies that criteria I articulated at the beginning of having long-lived liquid water. But it's not a planet. It's a moon. And here's a kind of a mosaic of different objects in the solar system that I think if you showed these, to grade 6 kids and you said, what are these? They would say, those are planets, right? Why? Because they're big round objects that look like planets. And some of them are, but some of them aren't, right? The distinction between what's a planet and what's a moon is just, does it orbit a planet? If a thing orbits a planet, it's not called a planet, it's called a moon. But if it orbits the sun, it's called a planet, right? But that doesn't mean that the object itself has any particular set of properties. So I encourage you to kind of look at this image and decide for yourself which ones are planets, which ones are moons. I'll give you a second to kind of think it through if you like. All the ones that are just sort of featureless and beige, those are objects that are known and we have a sense of what their size and their shape are, but we haven't got close-up pictures of them. So they're real objects, we just don't have good pictures of. Okay, so here are the results. So you can see that this is a real mix, right? The first large object on the left there is the planet Mars. But the next one is a moon of Jupiter called Ganymede. The next one is a moon of Saturn called Titan, and then the planet Mercury. So there are 2 moons in our solar system which are bigger than the smallest planet, right? And then you just keep going. There's Callisto, that's a moon of Jupiter. There are some dwarf planets. There's, all sorts of things in our solar system that at first glance you would say that's a planet. And I think it's really important for us to consider these when we think about where could life exist in the universe. Because in our solar system, there is one planet that sustains long-lasting water, liquid water. But there are like 5 moons that have significant liquid water that has been there for millions of years. So if your criterion for finding a place that's suitable for life is there needs to be liquid water, then 5 times as many objects that satisfy that criterion in our solar system are moons than planets. So let me show you a couple of those. This is a kind of a bit of a grainy image. It's a moon of Saturn. And these bright bands you see across the center of the image, those are the rings of Saturn, okay? This is a moon, the kind of grayish sphere in the center is a moon seen in silhouette. It's called Enceladus. And at the bottom of that moon, you may be able to see these kind of faint plumes of light. Those are geysers, like, Yellowstone in the United States. They're jets of water shooting out of that moon because Enceladus has an ocean. In fact, this moon of Saturn has more liquid water than Earth does, as far as we can tell. And there's even some chemical evidence in those geysers, those plumes, that it has hydrothermal vents at the bottom of its ocean, just like Earth does. And on Earth, we're not totally sure, but a going hypothesis is that those hydrothermal vents are the place where life first evolved on Earth. So Enceladus appears to have hydrothermal vents, and it certainly has tons of water. Is it Earth-like? Not really, not in the sense that you or I would want to live there. The exterior of the planet is solid ice, and it doesn't have much in the way of an atmosphere. But for aquatic life, it could be a paradise, right? It's a huge volume of water that seems to be kind of chemically enriched from the planet, like the oceans are on Earth, and potentially hosts life, just not necessarily life exactly like us. So because of this potential for moons to host life, there are a couple of missions heading to the outer solar system in the next few years. In just a few weeks, it's expected that the JUICE spacecraft, which JUICE, I believe, is Jupiter Icy Moons Explorer, will be launching to Ganymede, a moon of Jupiter, in about 3 weeks. And it will study Ganymede, which has, like Enceladus, has oceans beneath an icy surface. Next year will be Europa Clipper, which will be going to a different moon of Jupiter called Europa, which also has oceans. Now, these are orbiters, they're not landers, and they're certainly not going to, burrow into those oceans and swim around for a variety of reasons. But they're going to orbit those moons, and by orbiting them repeatedly, they're going to be able to give us a sense of what is in those oceans, kind of, what state is the water in? Is it truly liquid? Is it slushy? What are the chemicals in that water? Things like that. So they'll start building up a sense of what these moons might be like. And if you think about the universe beyond, right, there are at least as many kind of gassy planets that have typically lots of moons as there are rocky planets. So it's entirely possible that the first life we find beyond our solar system may not be on a planet, but on a moon. Lewis asked a great question. With our current technology, would we be able to detect exomoons via the transit method? So an exomoon is, a moon of an exoplanet, right? It's a moon orbiting a planet in another solar system. And indeed, you can detect exoplanets with the transit method. Basically, the moon also blocks some light from the star, and you can see the signature of that. There are a few candidate exomoons already known. People argue whether or not they're true exomoons, but there are some candidates already known. And as you say, right, you say you assume only if the moon was almost the size of the planet, and that is indeed the case. For the exomoons that are currently, or the candidate exomoons that are currently known, they are quite large. So for example, there's an exoplanet known that's around the size of Jupiter, which has a moon that is around the size of Neptune, or at least potentially has one. More data is going to be needed to kind of confirm those interpretations, but we will soon be in that realm of identifying not just exoplanets, but exomoons. Okay, so where is all of this going? Well, here's a kind of timeline of space missions that were designed to, in some way, contribute to this search for another Earth-like planet. You can see among recent ones, in 2013, was the Gaia Space Telescope. Gaia is doing something that doesn't initially seem to have anything to do with the search for an Earth-like planet. It's mapping stars, billions and billions of stars. You may have seen for many years now pictures from the Gaia spacecraft to these gorgeous visualizations of our Milky Way. But one of the things it's doing as it looks at all of those stars is checking them for planets. So very soon, we expect to have an enormous number of new planets added to our catalog by the Gaia spacecraft. The James Webb Space Telescope, of course, is up. And there's also some missions that are coming, Plato and Ariel. Basically, in the relatively near future, we will be launching more telescopes that are optimized specifically to either find or characterize exoplanets. And as technology develops, we will go from characterizing mainly gas giants, which are easy to see and easy to characterize, but less likely to be useful life for hosting life, toward being able to characterize Earth-like exoplanets. What it may take to truly characterize an Earth-like exoplanet would be a constellation of telescopes in space, a big group of telescopes that are spread out over, a large chunk of the solar system and work in concert to take detailed images of exoplanets, which is technologically possible, but just kind of tricky at the moment. We need, both to find out how to do that in a cost-effective way and also to be able to coordinate a large network of space telescopes. They have to be coordinated very, very precisely for this technique to work. But it's a well understood technique, and it'll basically just take time to kind of hammer out the engineering to make it happen. And then as a parting thought, there is one other way we could find an Earth-like planet. And it's a long shot, or maybe it isn't, but it feels kind of like a long shot. And that is to just find an Earth-like planet that has people on it that want to talk to us. So this is something that astronomers are actively doing, right? There are a small number of telescopes in the world that have been built that are optimized to search not just for a planet, but for an inhabited planet with intelligent life that wants to communicate with us. You may have seen very recently, there was a big kind of a news flurry about an undergraduate student at the University of Toronto who published a study of how to use some of these novel machine learning techniques that are being increasingly used these days to sift through the enormous amount of data generated by these telescopes and look for signatures of extraterrestrial intelligence. So that is one of the frontiers astronomers are exploring, trying to find planets out there that might in some way be called another Earth. Okay, so that's everything I wanted to share with you today. Thank you very much for your attention. And I very much welcome any questions you may have. You can go ahead and type them into the chat, or Julie may be able to let you unmute and ask them directly.
Yes, thank you very much. First of all, always interesting. I love your talks all the time, but this one really polished, lots of information on it, and it's great to get the latest info as well. I really appreciate that. Yeah, I think people can unmute. Hold on, I'll double check. But yes, you can unmute yourself if you'd like to ask a question directly. So please go ahead if you'd like to do that. We welcome that. But yeah, lots of interesting info on this topic.
Thanks very much, Joanne.
Yes, thank you for being there. Actually, as people are maybe either typing or thinking about it, I just want to mention we've been Discover the Universe for the last 2 years has been working on educational resources on exoplanets. We received funding from the Quebec government to do it with IREX in Montreal, the Trotti Institute for Research on Exoplanets. It's all in French now, but we're hoping to translate. I think they're working on translating it, and we're hoping to translate that. I'm just going to put it in the chat if you'd like to see. I don't think, Mike, you've even seen that page. It's just new. Some parts are still coming, but there are lots of resources in there, some videos, some activities, some cards. I especially like these cards. I have some, there are some of the older versions, but like little cards on exoplanets that you can sort or look at. And I think this is the first thing that's being translated. So something's coming soon on Discover the Universe. That might be interesting for all of you.
Okay.
Well, I think I'm going to stop the recording right here. So thanks, everyone. If you watched the recording till the end, thanks for being there.